Thank you very much for having me. I just want to say quickly that there's going to be a little bit of repeat from some of the things that were discussed today, specifically from Marina and also Linda with the problem shifting and things like that. But it's nice to see that we're all on the same page somehow, and maybe researchers and business were not so different after all. Maybe we just look at things slightly from a different angle. So I'll just explain a little bit more about that here. So how circular is Norway's bioeconomy? Now, I'm not going to be talking about all resources in the bioeconomy. Here, I'm specifically talking about phosphorus, and that's something very close to your heart, and energy aspects related to the phosphorus question. But in order for us to understand how circular we're using phosphorus or how circular our bioeconomy is, we really have to move away from this singular industry approach where we say, right, okay, I have my company, I have a lot of side streams, I have byproducts. How can I recycle that in the best way? Find recycling streams, find ways to use this stuff and call it a job well done, end of the day. And the reason why we have to move away from this singular industry approach or singular sector approach is because we're not working with singular sectors. Our society is much, much more complicated. Our society is, in fact, a very complex system of resources and emissions, where, as Linda explained very well earlier, if we start moving around resources in one part of the value chain, we'll very likely end up with problems elsewhere. And that can be resource issues or emission issues, as we can see from here, this figure here. Now, if we take this systems analysis approach, this is kind of a systems perspective here, and we think about the Norwegian bioeconomy, there's a few things we care about with the Norwegian bioeconomy. And this is not an exhaustive list, but this is just to show you a little bit about the things that we consider making sure we have a circular use of, and that's nutrients, energy, can you see, am I in the way? Water, and land. Now, as I mentioned in the beginning, I'm going to be speaking exclusively about nutrients and some energy aspects as well, and more specifically about phosphorus. Now, phosphorus is super important, and Marina talked a bit about why it's important, but I'll go a little bit more in detail. Phosphorus is important because it's a critical plant nutrient. We absolutely have to have it in order to produce plants. And the other issue with phosphorus is that that's a mistake, but anyways, it's supposed to say phosphorus is not equal to nitrogen because it's irreplaceable. We can't just, when we run out of phosphorus, we can't just say, oh, let's just use nitrogen, because it doesn't work that way. We need phosphorus in the right amounts and in the right form. The next issue is that phosphorus is limited. We mine phosphorus, and the largest amount of phosphorus is located in geopolitically unstable areas such as Morocco and occupied Western Sahara. So it's really important that we have access to this resource because we need it to create all food. It underpins all food system, and very plainly put, without phosphorus, we do not have any food, which means that without phosphorus, we cannot reach our sustainable development goals. Now, the issue here is that, as we all know, because we do not have a circular economy at the moment, we use phosphorus extremely inefficiently globally. Norway is maybe a bit better than others, but in general, we're quite inefficient at the way we use phosphorus. We mine it, we produce fertilizer, we put it on our fields, usually in excess. A lot of this phosphorus accumulates in the soil. Some of it gets washed away into water bodies and causes pollution. Now, this is an effect that we have from having too much phosphorus in oceans, and that's an environmental phenomenon called eutrophication. Now, this is the Gulf of Mexico here, and I think currently it holds the record for the largest dead zone area in the world. And what that means, it's maybe not something to be proud of, but what that means is that in this area, because of over-eutrophication in specific agriculture, this area of the Gulf of Mexico cannot support life. It's been depleted of oxygen due to eutrophication. And what happens is when these algae blooms come, they die, they take up oxygen when they degrade in the ocean, and then there's no oxygen left for the wildlife. So you see often these big fish kills these are a bunch of fish if you can't make out what that is. You see often these big fish kills, and this becomes a problem for kind of all parts of society. Now, how do we address this? What can we do as researchers or as businesses or what have you to try to help the phosphorus situation? We can try to optimize its use. We can try to reduce the amount of waste that we have. We can try to reduce the amount of emissions that we have. And we can do this using a tool called material flow analysis. Now, that's a tool that I work with in my research, and Kirsten mentioned it briefly. But just to give you a few more details about it, what we do in material flow analysis is we use the systems approach as kind of the baseline. So we try to understand a system and map it, try to understand how resources flow through that system. Then we take data, and the data can be from statistics or industry or whatever, and we map this onto our system. Then we produce models and scenarios. We say, okay, this is what this looks like today. What could this look like in the future, assuming specific technological trends or what have you? And then, of course, we always have to do this in light of uncertainty, because every model is inherently associated with uncertainty. So we need to understand how robust our numbers are before we say, okay, here you go, industry, here you go, policymakers, do something with this. And then we, of course, produce visualizations, which you'll see some in a minute, and try to make indicators that are actually good representations of how efficient the system is. And then at the end of the day, we like to sum all of this up and hopefully provide some strategy and decision support. Now, it's best to show using example. So here I have this system of Norwegian phosphorus use in Norway. And so what we've done is we've looked at crop production, meat and fish production, food processing, and human consumption. And we tried to understand how much phosphorus is going through being consumed by each one of these industries, how much is being lost, and what are the drivers. So what are the big hotspots where we can focus on to try to optimize resource use? So we quantified this system, and this is very complex, and I don't expect you to understand it immediately, but I'll just focus on some key results. Here we have crop production. Oh, that's also not good. That's supposed to be a delta. But anyway, so crop production. So at first sight, we see, oh, it actually doesn't look that bad. I mean, most of the phosphorus going into the system is being returned at some point back to cropland or to soil. But if we take a closer look, we realize that the picture is not so simple. Most of this phosphorus is not actually being used by crops. Instead, it's accumulating in soils. So technically, we're recycling phosphorus from these different secondary products, but we're not using it very well. So that's one of the key takeaways, that returning things is not the same as recycling. Now, if you look at aquaculture, the situation looks much, much worse. It's very clear that most of the phosphorus that we put into aquaculture in the form of feed is just lost straight to water bodies. And that's because we have excess feed and we also have excrements. So in Norway, we produce fish in fjords, and the fish intake feed, and then they excrete it out into the ocean, and it's very, very difficult to get this phosphorus back. Now, with the expected growth in the aquaculture industry, I guess most of you are familiar with Norway's ambition to quintuple aquaculture production by 2050. We tried to understand, okay, well, if this is a situation now, what is it going to look like in 2050 with all this extra fish production? And we see that this is the baseline here. These are the Norwegian secondary phosphorus sources that we have today, and then what we have in the future. And we can see that originally we had manure as the primary secondary source, and that's something you talked about wanting to use in your Yara business model. But in the future, the secondary phosphorus sources are really going to come, if we do quintuple fish production, it really is going to come from aquaculture, and it's not really going to be manure anymore. The big potentials will be here. We have the other potentials: sewage sludge, fish scraps, dumped fish scraps, fish scraps, exported fish scraps, and dumped fish scrap. And you can see that at the end of the day, those are kind of, we call it pennies. They're not worth much when you compare it to the big players here. And this is important because as we increase our aquaculture production and as we increase the amount of phosphorus just going into our fjords, we're also increasing the likelihood that we'll experience eutrophication events. And this is a global study, so this is not Norway specifically, but we do see that fisheries and aquaculture are a huge driver of marine and freshwater eutrophication. So as we increase aquaculture and fisheries production, so does the eutrophication footprints go up. Now, so if we revisit the first question that I asked, how circular is Norway's bioeconomy? Well, it's kind of a definition issue. Does return equal recycling? I don't know. How do we define this? But if I had to put a number on it, in terms of phosphorus, I say roughly 50%. But how useful is this exercise? Is this really what we should be talking about? Is 100% recycling always better? That I would like to offer a bit of caution here. I'm going to show you, and this is something that was picked up by basically every speaker today, so I feel like I'm just speaking to the crowd. Everyone knows this. But I'm going to show you very specifically how a circular economy leads to a lot of challenges, and perhaps we should approach a circular economy with caution, do a cautious circular economy model rather than just a die-hard circular economy model. Now, not all phosphorus is made equally. There is a big question when it comes to quality. We need to make sure that the products, the secondary products we have, can actually replace primary products. And when we look at the quality of secondary phosphorus products, they vary widely. The diagonal lines here represent the amount of phosphorus in these products that is actually available for plants to use. So it's a good indication of whether we can actually use this stuff as mineral fertilizer substitutes. And for most of the secondary products, it turns out they're very bad substitutes for mineral fertilizer. So if we think about it, if we take sewage sludge, for example, most of sewage sludge phosphorus is residual phosphorus, can't be used by plants, not in the first growing season anyway. So if we just add this phosphorus to the soil here, most of the phosphorus will just accumulate in the residual phosphorus pool, which then just increases the likelihood that we'll have runoff and then experience eutrophication. So we should be really careful with how we use our secondary products and make sure that we understand their substitutability very well before we implement different recycling. I'm not saying people do this, but this is just an illustration to show that this is a risk. So if we correct our secondary phosphorus potential in Norway based off of the quality, the potential decreases dramatically. We can see that most of the products do not represent very good secondary phosphorus or fertilizer replacements. And the picture gets a little bit more complex when we think about energy. So we use the same exact approach, the mapping approach, but instead we mapped energy on top of phosphorus to try to understand what are the energy implications from recycling phosphorus. How can we make sure that phosphorus supply and demand meet each other without needing primary materials? And what we found out that it's really not that easy. And the reason why is because most of the supply is in the western part of the country, and most of the demand is in the eastern part of the country. So if we think about transporting this stuff from one place to the other, we might do really, really well with phosphorus. Okay, we've recycled very well. We have a circular phosphorus economy, but we've done so at the expense of our emissions. So that's something that we have to be really conscious of when we're trying to understand how we can create a circular economy. So with that, I would like to go to my conclusions. I hope I've illustrated that the circular economy is a really interesting way to structure our economy. It's a very good tool and a good way to think about how we should use resources better and definitely not increase our resource use in the future. However, we have to keep in mind that this is not a goal in and of itself, but rather a means to an end, where the main goal is really to make sure that we can reach the Sustainable Development Goals and do so without sacrificing other Sustainable Development Goals. And material flow analysis, the tool that I presented to you today, is a really good tool for trying to understand the trade-offs between the different sustainable development goals, where we can understand that, okay, maybe we'll fix one thing, we'll be able to feed the world, but we'll do so at the expense of our climate. So this tool, I would like to urge those of you that don't know about it to maybe look into a little bit of how you can use it in your own companies, because at the end of the day, it can help you streamline your business model. It can help you utilize your resources the best way possible, and it show you where the inefficiencies in your business lies. So with that, I would like to thank you for your attention, and these are the references that I used. Thank you.